Welcome to this introduction to solar orientation. We'll start by exploring the reasons for the seasons and see how the sun's path across the sky changes during the year. Then we'll find out how to measure the sun's position in the sky and how to chart how its position changes through the seasons. Finally, we'll look at the two different North Poles and learn about other resources for exploring solar orientation. Let's get started. Solar orientation is basically the process of aiming something at the sun. This is important because any solar technology like a solar panel or a sun oven or even a passive solar home receives the greatest amount of energy when pointed or oriented at a direct 90-degree angle toward the sun. This isn't as easy as you might think, however, because the sun's position in the sky is constantly moving. It rises in the east, arcs across the sky, and sets in the west. Not only that, the sun's actual arc across the sky changes position throughout the year. In the winter in the northern hemisphere, the sun's daily path across the sky moves lower toward the south. This isn't a problem with something like a solar box oven. You just face it toward the sun and move it when needed to follow the sun's movement. However, other solar technologies, especially solar homes, need to use the seasonal changes in the sun's position to work properly throughout the year. Because of this, solar home builders need to know where the sun will be in the sky at any time of the year. This is the first step in deciding whether a specific location is a good place to build a solar home. It also helps us estimate how much power we can get from a solar electric system at that location. Let's find out how to chart the sun's position throughout the year and see why proper solar orientation provides more energy. We'll start by exploring the reasons for the seasons. We all know it's hotter in the summer, but why is that? You might think it's because the Earth is closer to the sun, but actually the opposite is true. Besides, when it's summer in the northern hemisphere, it's winter in the southern hemisphere. So why is it hotter in the summer? It's hotter in the summer because the sun's path is higher in the sky. This results in two things. It makes the days longer, and it makes the summer sun more intense. To see why the summer sun is more intense, let's use a flashlight for a simple demonstration. In a darkened room, shine the flashlight on a flat surface at a direct 90-degree angle. Notice the size of the area lit by the light. Then angle the flashlight down to a less direct angle. The size of the lit area increases, but the intensity or brightness of it is reduced. The more direct 90-degree angle provides the most intense light. The same thing happens with the sun. The higher it is in the sky, the more direct and intense the sunlight will be. So why is the sun higher in the summer? To find out, we need to remember two things. First, the Earth is tilted on its axis. And second, the Earth is orbiting the sun. Every year, the Earth travels around the sun in a huge circular path through space. During summer in the northern hemisphere, the North Pole is tilted toward the sun. This makes the sun's path higher in the sky and causes the northern half of the Earth to receive more light and heat than it does during the winter. On the first day of summer, around June 21st, the northern hemisphere is tilted the most toward the sun. This is called the summer solstice, and the sun's path is higher in the sky than it is on any other day of the year. Because the sun is in the sky for more hours, the summer solstice is also the longest day of the year. These extra hours of sunlight give the sun more time to heat the Earth. This is the main reason that summer is the hottest season. As the Earth continues its orbit, it reaches a point where it's tilted sideways to the sun. This is called the autumnal equinox. Both the day and the night are the same number of hours. The Earth reaches the other side of the sun on the shortest day of the year, the winter solstice. This is the first day of winter, and the northern hemisphere is tilted farthest away from the sun. As the Earth travels back toward summer, it passes another point where the axis is tilted sideways to the sun. Once again, day and night are the same length. This day is called the vernal equinox. Let's see how this looks from the Earth's surface. We can think of the sky as a huge dome above our heads and imagine the sun's path traveling across the inside of this sky dome. On the surface of the Earth, we'll place letters for the four compass directions: north, south, east, and west. Remember, the sun's path is highest in the sky on the summer solstice, the longest day of the year. Its path is lowest on the shortest day of the year, the winter solstice. If we draw the sun's paths on these 2 days, we can clearly see why the day lengths are different. The sun's path across the sky is longer in the summer and shorter in the winter. The longer the path, the more hours the sun is in the sky. Throughout the year, the sun's path will move up and down between these two extremes. We can now begin to chart where the sun will be at any time of day during the year at this location. At 9 in the morning on December 21st, the sun has risen in the east and is low in the southern sky. On June 21st, it's higher in the sky at this same time of day. We can draw a line on the sky dome between these two 9 a.m. positions. This line shows where the sun will be at 9 a.m. during the rest of the year. As the sun's path moves up and down through the seasons, the position of the sun at 9 a.m. will always be somewhere on this line. Likewise, we can draw a line for the sun's position at 3 p.m. Throughout the year, the position of the sun at 3 p.m. will always be somewhere on this line. We now have a rectangle on the sky dome showing where the sun will be between 9 in the morning and 3 in the afternoon throughout the year. On any day of the year, the sun's arc across the sky will be between the two white paths. Between 9 a.m. and 3 p.m., it will be somewhere between the two yellow lines. The area inside this rectangle is called the solar window for this location. The solar window is important because the hours between 9 a.m. and 3 p.m. are when you get the most energy from the sun. To receive the maximum solar energy, you don't want the solar window to be shaded by trees or other obstacles between 9 a.m. and 3 p.m. during most of the year. Before installing a solar electric system or building a passive solar home, builders and installers analyze the building site's solar window and see if there are any shading obstacles. To chart the boundaries of the solar window for a real location on the Earth's surface, we need to know how to actually measure the sun's position in the sky. To do this, let's imagine we're standing under the exact center of the sky dome, and that the sun is somewhere on the inside surface of the dome. The sun's position on the sky dome is a combination of two measurements. The first measurement is the sun's direction on a compass. A plumb line drawn from the sun to the horizon intersects a specific degree on a compass rose. This angle is a measure of the sun's azimuth. We also need to know the sun's altitude or vertical angle, its angular height above the horizon. The combination of azimuth and altitude describes a specific spot on the sky dome. We can use these same two measurements to describe the real sun's position in the actual sky. Then we can draw charts that show how the sun's position changes throughout the year. This kind of chart is called a sun path chart, and it shows what the sun's path looks like from the Earth's surface. This is a sun path chart for San Francisco, California, and it shows what we'd see if we looked toward the South Pole at this location. On the left side of the chart, we measure the sun's altitude, or height above the horizon. This is also called solar elevation. It starts at 0 degrees at the horizon and goes up to 90 degrees or directly overhead. The bottom line on the chart measures the sun's direction on a compass. The center of the chart is 180 degrees or due south. The intersection of the sun's altitude and azimuth on the graph shows the sun's position in the sky. We can overlay the locations of shading obstacles like trees or buildings. Here we've also overlaid the sun's paths on the shortest and the longest days of the year. We can also graph the position lines for the hours of the day. This shows the solar window, the area of the sky where the sun will be between 9 a.m. and 3 p.m. throughout the entire year. Finally, we include the monthly sun paths for the rest of the year. There are only 5 more paths because the sun's path is duplicated as it moves up and down through the seasons. For example, its path on March 21st is the same as its path on September 21st. Now we can see where the sun will be shaded during the year. Notice the lowest sun path, the path for December 21st. Between 9 and 10 a.m. on this day, the sun will be shaded by a tree that stands between 135 and 155 degrees on the compass rose. The University of Oregon has an online program for creating sun path charts like these for your location. It's available for free at this web address. After making the charts online, you can print them out and check them at your location to see if any obstacles will shade your site. To do this, line up the south or 180-degree measurement on the bottom of the chart with true south at your location. You can find south with a compass. Just align the compass needle with north on the compass rose, and the other end of the needle points toward south. But remember, it doesn't point toward true south. There are actually 2 north and 2 south poles. A compass needle points to magnetic north, not true north. Magnetic north is a location in northern Canada. True north is one end of the axis around which the Earth rotates. The difference between true and magnetic north is called magnetic declination. The United States government has magnetic declination maps available online on the National Oceanic and Atmospheric Administration web address shown here. These maps are updated regularly because the position of the magnetic North Pole is slowly moving. The Rahus Institute publishes the Your Solar Home Guidebook. It has complete directions for using these maps to find true north with a compass and is available at www.rahus.org. The guidebook also includes templates and instructions for simple projects for measuring the sun's altitude and azimuth. The templates are photocopied and then cut out and folded to make inexpensive tools for plotting the sun's position. You can check your actual measurements against your sun path charts. This concludes our introduction to solar orientation. If you'd like more information, please visit our website at www.solarschoolhouse.org. Best of luck and have a sunny day.